SatNOGS, so it's a network, an open...
It's a network of a ground station, but it's built by enthusiasts. It's a community of a ground station. So first, hello everyone. My name is Julien NICOLAS. I am a contributor of this project, and I am a volunteer on this project. So it's only for fun, and also to build something that is useful to people, and but there is no money involved at all. So first, in the sky today there is a lot of objects all around Earth, more and more objects. There is geostationary satellite, and also all other satellites that are moving from our point of view on Earth. And for example, the LEO orbit, where there is a lot of satellite today, the CubeSat satellite, for example, are moving from the point of view of Earth. So to be able to get data from them, we need tracking. And because they are in line of sight in a very short amount of time, it makes sense to build a network of ground stations, because you need to share the antenna time of your ground station, because the satellite will be in line of sight during maybe 10 minutes or less. So this project is about this, building a ground station network in which everyone can add his own ground station. So today the network looks like this. It's a view of the network. The satellites pass in the sky, and the ground station track it and record the data. The coverage of the network is quite wide, so we can sometimes even track from two different ground stations the same satellite. It enables us to do continuous tracking sometimes. So here you can see the green line is the satellite path in the sky, and the green dot is the ground station, and the purple or the orange line is the data connection between the satellite and the ground station. And the color is depending on the frequency. This is a map that is made real time in a 3D. It's a 3D view. It's a 3D real-time view of the network activity. But it's only a screenshot for here. But I can show you it real time if you want. So how does it work? It's really easy. There is a global network management that the user asks the network to do an observation, and all the ground station ask the network what the jobs are needed, and then the ground station do the tracking of the satellite, save the observation, and send it back to the network. And then the user can fetch the observation on the network. So today the network is like this. Green dot are ground station. So the coverage is quite wide. So it works with 3 different parts. The ground station itself, the network, and the database. First, the network. It's a web application made in Python, where the user can ask for an observation and also get the data from an observation. Then there is a ground station itself that is made with a small single board computer, like a Raspberry Pi, and of course a SDR receiver and an antenna, and sometimes 2 or more different antennas to be able to do receiving in different bands. On the small single board computer, there is a GNU radio that does the data processing. On the other hand, the database holds all the data from the observation and also all the transponder data, because it's very important to have a database with all the frequency and the modulation of every satellite. And we also have a data warehouse, and we can do a graphical analysis of the data, of the observation data. From the point of view of the ground station owner, when you want to schedule an observation, you have all the past prediction in the sky above your station from the next 3D. And you only have to click schedule, and it will program the observation in the next 3 days or so. So you have the path in the sky, you have the name of the satellite, if the previous observation were successful or not. It's the little green bar or red bar. You have the path of the satellite in the sky, and you can also see if there is an observation that are overlapping your previously programmed observation. And then, if you are, for example, a satellite owner, you can also schedule observation on the wide network in one time. Basically, you only have to give your satellite name, what transmitter you want to listen, and the time window, and it will give you all the ground stations that will be in line of sight of the satellite during this amount of time. So you can have the bar which corresponds to the line of sight of the ground station during the time of the ground station, and you can see that there is overlapping of the observation, which is very interesting because we will not lose at all data. And when you click schedule, it will create the job on every ground station of the network. So the ground station is made with a Raspberry Pi, an SDR. You can also use a higher-end SDR, for example, USRP. You will also need an antenna. On our website, we provide open source design of different antennas that are well designed for this purpose. We also provide a rotator design, which we can have a look in the entrance. And also, if you want, you can also use omnidirectional antenna, and so you don't need an antenna rotator. Everything is on the wiki. So when it's finished, it looks like this: small computer, power over Ethernet, and also an LNA and the SDR, which is here. So it's a quick example of the design, the mechanical design of the rotator, that you can find it on the wiki. To build it, you only need a 3D printer. So it's an example to show how it's well documented. When it's finished, it looks like this, with also an open design antenna. But you can also use commercial gears. So it's fully compatible with commercial gears, antenna rotator from Wimope, for example. So now, the signal processing that occurs on board. So all the signal processing run on the small Linux computer, the Raspberry Pi. So there is not a lot of horsepower available to run the flow graph. So we need to have a few tricks to be able to do it. We have one GNU radio flow for each modulation. Today we are able to decode quite a lot of different modulation, but it's near always the same. We also are able to demodulate the weather picture from the NOAA satellite. So like in every GNU radio flow chart, it's near always the same. We first do the raw data acquisition from the hardware. So we use Osmo SDR, but we are currently developing the SWAPI driver to replace it and to be able to use near any SWAPI peripheral right out of the box. So today, this OutofThree module is usable. You can use it. It works very well, but it's not fully implemented in our network. We are currently testing it. Then we do the resampling to be able to run everything on this small single board computer, and it's still sometimes crash. And then we do the Doppler correction. So for this, we have a custom block that in our OutofThree modules. After that, we do the demodulation. So it's vary on the GNU Radio flow graph that it's being run. For example, there is little more than demodulation sometimes when, for example, for the weather picture decoding. We also do the waterfall generation in this GNU Radio flow graph. It's a custom block that write a data file, and then we process this file with a matplotlib script. We do also the IQ dump, but we don't do it on every observation because of the size of it, and also to the where because it will destroy the SD card of the Raspberry Pi quickly. We only do an audio dump of the raw data because it's very useful because we have a lot of tools that enable us to process this intermediate frequency that is written inside the audio file. And also we write the data output file with all the decoded data. Donc for example, in AX25, we will see the raw packets. So for example, the Morse decoder look like this. We have the data acquisition here. Here, the Doppler correction that is made with the input that are from our script that generate a RigCTRL message. Then there is filtering and processing of the data. So it looks like every time the same. It's it. On the ground station point of view, you can also use it in a standalone way. This enables you to do your own observation without sending anything to the network. So basically, what is it? Is that you can run any GNU Radio flow graph with a Doppler correction, and you only have to provide the TLE, which is the orbital parameters of the satellite you want to observe, and the flow graph, and when you have to run it, and it will run it automatically and do the Doppler compensation. So these things can be totally used, for example, for radio astronomy, for example, or anything else that's the first purpose of it. There is also, when you are in standalone mode, a way to send command to satellite that is suitable only for for a satellite team, for example. It uses only GNU Radio, and it enables you to send TeleCommand to a satellite. And it was used with success with the UpSat satellite 2 years ago. And this is also fully open source. So if you are building a CubeSat, you can totally have a look on it, on how it works, and use it in your project. A typical observation looks like this. You have the name of the satellite, the name of the station, and a way to say if the observation is good or not. And you have the waterfall on the right. You can see the data that is successfully Doppler corrected in the center, right and really straight. And there is 2 other signals that are from another orbit or maybe from the Earth that are wrongly Doppler corrected. So you can know that it's not the satellite you want to receive. An example of the data you have in the observation. So there is a data table, and inside there is all the raw content of the packets. Also, you can download the audio file of this recording, for example, to be able to do processing later on it. Another example of a more special observation, it's a weather satellite picture. So the waterfall looks like this, and then it automatically decodes the data, and you have a picture. This one is not perfect, but it's a picture. Also, something very important at the end of the project is to do something with all the data we decode from all these packets, because a lot of telemetry packets have very useful information in it. So we aggregate all the data to be able to make a real-time telemetry display, and it's useful also for satellite teams. And we can even send alert email with this. You only have to give a criteria on to make an alert. For example, this is it's totally real time, and it's network wide, so it's Earth wide observation. Like I said previously, the big problem with satellite is that all the information about frequency and modulation is not in a central place. It's everywhere on the internet, on the satellite website project, and sometimes it's very hard to find. So we built a database with all this information, and this database is totally open to contributors, and it's very important that everybody can contribute to it. So we have something very complete. The network is very wide today. We started in 2014, so it's quite old today. There is more and more ground stations on the network. Every day there is about two new ground stations on the network. So now, to come back to the GNU radio, we have several OutofThree GNU radio modules. The first is a SatNOGS OutofThree module, which are the custom blocks used for the project. So it's enable you to do the Doppler correction and a few other useful things. We also have the GNU Radio SWAPI module. So you can use any SWAPI device in your GNU Radio flow graph. It's also useful to be able to use a remote peripheral on your network, and it works very well. We also have a GNU Radio module for LEO. It's a space channel simulator which enable you to do simulation of the transmission between Earth and an object in the LEO orbit. We also have a CCSDS implementation, which is a recommendation for telemetry and TeleCommand protocol. So basically, if you are building a satellite, you should take a look to this, because you can implement a way to send telemetry and TeleCommand in a very open way, and in something that will be very useful in the long term in your project. To start to have something that is a bit unified. So you can join us and build a ground station. You can also contribute to the community. You are also welcome to use all these GNU Radio OutofThree modules and to contribute to them. So thank you. If you have any question.
Okay, we are ready for your questions. I may start with a question. You're a ham radio guy? Yes. So how many people are from this community in here? Well, okay. It's a very, very interesting community that is really used to share their knowledge with other people. And that's, you find a lot of people working with GNU Radio in the ham radio community, so it's quite interesting. Yeah.
And there is something special to mention about this. Is the new geostationary satellite that we have is a very nice playground for SDR, because we have uplink in the 2.4 gig band and downlink in 10 gigs, and it's the perfect use case, for example, for a Pluto SDR to do the uplink and the downlink. And there is a lot of things to try, but of course, get the license first.
Okay. Thank you. I would like to ask a question. So I think that this is very interesting also for radio astronomy. And one thing that would be very interesting for radio astronomy, especially if we take inspiration on the new results of the black hole picture and everything, would be to have a sort of a phase synchronized set of receivers that you could use them together to, I don't know, to observe things in the sky and to make measurements. Would that be feasible, or is that possible? Have you ever thought about this?
Yes. For this, the problem is to be phase synchronized over a wide area. It's quite impossible, because the best way to do it is to have common signals that you receive and you lock on the phase of these signals. So, for example, a TV transmitter or anything like this. But for something very wide, I think it's very hard. And also about the radio astronomy part of this, today in our network, we always do the Doppler compensation. So it's a big problem for this. But we also have the need to be able to find which satellites have which TLE. Because when there is a launch, often there is a TLE lottery. So we want to be able that the network will be recording all the data, and by the analysis of this data, we will be able to find which TLE are which is objects. And it's something that will be very useful for all the community. Today we do this by hand.
Hello. If I understood well, the processing of the data is done on board, on the Raspberry Pi, on the ground station.
Yes.
So only one user can use one ground station at a time. Yes. Is that a crazy idea to do the processing on the client side instead of in the ground station?
On the server side?
On the server side, yes. So that
it will be interesting to only have the raw data that are going on the network. The problem is that in a lot of parts of the world, internet connection is not cheap. And you want to really send the smallest amount. For example, if I go in the network, if you to see that, for example, we have a ground station in Smile Island. It's not an error. Huh? So here, it's quite, internet is not cheap, for example. Also in Kazakhstan, internet is not cheap. For example, in South Africa, internet is not cheap. So the problem is here.
Just I'm using the SatNOGS station in France, okay? And I tried to put another one in South America, in Guyana. And it's exactly what you said. Internet is not cheap. And finally, it was not possible. And I think for SatNOGS, the problem, not the problem, but the future, is to extend SatNOGS to Africa and South America. It's a really big problem to extend the coverage to a permanent coverage of the satellite. You know? So it's very interesting, but we need to make some efforts to work.
Yeah, yes, totally. In fact, in this area, the best is to have an association. For example, Hackerspace will have enough money and people to run it correctly. I think it's the only way to do it.
But we have to find people.
Yes.
To host the station in this place.
Yes, we are working on this.
Yeah, I will give you the mic right before. Actually, there was a second question hidden in my first question.
Okay.
I work in the IoT, on the IoT market, and actually I see a good application for such a system for IoT instead of satellite
Yes.
Data acquisition. Is that a project that you have thought about, or is this already an application?
Yes, it will be something to do, because an SDR on in lot of places in the world with a small computer and with internet, you can do almost anything. So it would be a great idea. For example, for LoRa application to have a gateway to the internet. And there is also a few open source projects to build network of this kind of thing. So maybe we can try to share our hardware with them. It could be a good idea.
Yes, thank you for this nice presentation and also for this wonderful project. Regarding this problem of internet access, wouldn't it be possible to transmit the data using a radio amateur uplink to broadcast the information instead of using the internet?
Yes, it will be a good idea, but it's quite hard to transmit data which are not your data when you are amateur radio. I think that it will depend on the country, but it's really true that, for example, if you use the geostationary satellite to do the data aggregation to get all the data at the same place with only a dish and a Pluto SDR that will send the data this way, it would be great, but I think it's a bit out of the scope of the amateur radio. I think there will be problem, but maybe it's something that we can start to try to find, but it's not easy.
I would actually second the idea of phase synchronized receivers throughout the world. In my case, I would be really interested in over web SDR, very low frequency signals for direction finding, but I'm sure Paul will have more to tell us about phase synchronization of multiple receivers, so that would be really exciting.
Yes, I think that the Kiwi SDR has something to say about this.